The name and the date on the paper. Last name first is helpful. Get all the cell phones put away. And in 1 minute, draw a cladogram for all orders of extant amphibians. Okay. Draw a cladogram for all extant orders of amphibians.
Do you happen to know the date for the
27th.
27th?
Draw a cladogram for all extant orders of amphibians. Okay, another paper, please. Another paper.
Yeah.
That should have been easy. Okay. We've gone over that in lecture. We've had the stuff in labs. It's very important that you study as you go rather than put things off for too long. Okay. There we go. Well, one of the reasons, yes,
Olivia said that we would be getting the reptile lab stuff today, or are we getting it tomorrow from her?
that had been handed out previously. I do have some extras with me.
Okay.
Or I thought I handed that out before.
Yeah.
At any rate, I've got a bunch of them up here.
Okay.
So after class today, please scoop them up. Also, does anyone need lecture handouts for amphibians and reptiles? Okey-dokey. Yep, so I've got plenty of them right up here. What are the three orders? Someone give me one. Urodela, someone else give me another one. Anura, and another one. Yep, very good. Arguably, those look rather different, don't they? The Sicilians, Coats, and Salamanders. And as I mentioned before, in addition to amphibians, extant amphibians being interesting in their own right, I think they're also very interesting for gaining insights into some of what happened in this very profound transition from primarily an aquatic existence to a more terrestrial existence. So, can we find something that looks and acts similar to what we think was going on for the ancestral tetrapod? Okay? And who's this? Order? Denotiona, okay? Quite unique in that they are limbless. In addition to being limbless, they are elongate. They're specialized burrowers, and they burrow using their head. Their head has something of a wedge-like appearance, which is good for sort of ramming into the soil and kind of wiggling back and forth and making a burrow. Now, if you're using your head as a bit of a wedge in a battering ram, it sort of stands to reason that it's going to have to be a pretty sturdy structure. And in fact, when you look at the skull of Sicilians, there's a lot of bones, and they're firmly connected to other bones to make a sturdy and rather rigid skull compared to the skulls of other extant amphibians. Now, when you're underground, it's dark. Not all Sicilians live exclusively underground, but a lot of them do spend a lot of time underground. If you're doing that, eyes don't do much good. So there's sort of two things going on. One is eyes aren't terribly useful if you're in perpetual darkness. But what's another potential reason for having a smaller eye? Yes?
You don't want to catch it on anything when you go to your earth.
Yeah, and kind of along a similar line. So you wouldn't want to injure the eye, right?
I mean, if it's moving its head to dig, having eyes white hair, what do you think is the best?
So what are all the Salamander?
Well, eyes are squishy, right? Compared to bone. Okay, so think of the mechanical properties of eyeballs compared to bone, and if you're jamming your head through soil, and if you've got a squishy structure, not very good, but if you've got a rigid structure, that's going to play out much better. So you see a very small orbit in Sicilians compared to other extant amphibians, where what impresses me is actually how much space there is in the skulls of both salamanders and Anura. Okay? This is an example of what order? Anura, okay. Lacking a tail. as an adult. There are some interesting exceptions, but those are super rare. Tail frogs, okay? And you commonly see a disparity in the size of the limbs such that the hind limbs are much larger than the forelimbs. And here's a rotted frog, a leopard frog, sort of a generic frog, if there is such a thing. And you can see a clear difference in the size of the hind limbs compared to the forelimbs. Also, the trunk is not very mobile in Anuran amphibians. And you've seen bullfrog skeletons, mainly in lab. And what is a distinction between that bullfrog skeleton that you saw and the skeleton that you saw of Necturus with respect to the vertebrae? Think back, yes?
I mean, the Nectarus had a lot more vertebra.
Right, okay. So all other things being equal, if you have more vertebra over a given distance, and if you have the same amount of mobility, you're gonna have a much more flexible animal if you have more vertebra rather than fewer vertebra. Not only do Anurans have fewer vertebra, their mobility is actually very limited. So you've got a double whammy there, few vertebra and very, very little mobility, and therefore no substantial lateral undulation. Now, mind you, the pelvic girdle is attaching to the vertebra right here. So we're talking about from here on up to the skull, okay? All this, from this bump on back, is the greatly elongated pelvic girdle, okay? And as you're well aware, many Anuran amphibians are very good at jumping, and arguably this morphology indicates that it is in fact specialized to enhance jumping ability. And this is what? Order? Urodela. And what genus? What genus? This is one of the ones that you need to know in lab. This can actually be found in the eastern US. Ambystoma. Okay, so this is actually a spotted salamander in the genus Ambystoma. They're pretty sizable salamanders. I think they're pretty little beaks too, with those spots on them. Kind of look like little clowns. Okay. And they've got a tail, and a rather large one at that. Now again, I'm painting with rather broad brush strokes here, but at least compared to Anurans, you have a greater similarity in the sizes of the limbs, as far as forelimbs compared to hind limbs. There's a significant distance between the fore and the hind limbs compared to Anuran amphibians. And when salamanders move, the vertebral column bends laterally. Now, in light of what we've just gone over for these three orders of amphibians, which one do you think is best suited for gaining insights into the ancestral tetrapodal condition? Well, let's just take a vote. Who says Gymnophiona? Raise your hands. Who says Anura? Raise your hand. Who says Urodela? Raise your hands. Okay, I guess we're unanimous, but then the next question is why? Yes.
Because they exhibit the tetrapod limbs, they have all four limbs.
Okay, and indeed, Gymnophiona doesn't have any, okay, so that's out in Never Never Land compared to the ancestral tetrapod. And somebody else?
Has a tail for the most part, like the back
It
of.
doesn't have a tail for the most part,
I
it's
mean,
got a tail.
I
And the darn big one. And early tetrapods had sizable tails too. What else is a key trait of interest?
The ability to do lateral undulation like the fish could.
Absolutely. So this is a very old vertebrate trait, using the axial structures for propulsion. Okay? So indeed, this group is quite well suited for gaining insights into what was going on in ancestral tetrapods. Not only because of its morphology, but also a handy-dandy thing is that salamanders move in water and on land, okay? So they do two key things, okay? So a lot of the studies on the locomotion of salamanders, or I should say urideals, because some of the locomotions have been on newts, has been to get at this issue of sort of how profound is this transition from water to land. Okay? So some key things you should be able to do regarding locomotion of salamanders is compare and contrast how they move on land versus in water. As I mentioned, they do both and do both reasonably well. And in particular, what's going on with respect to axial movements and axial muscle activity. Okay? After all, if fish bend from side to side when they're swimming, and salamanders bend from side to side when they move, have they simply retained all of this stuff that fish do, and they do just fine on land because they have legs in addition to these axial structures? Or does it appear that there's some evolutionary novelties associated with this transition from water to land? Okay? So another thing you sort of need to keep track of is you sort of have these two potential systems. The axial structures, the vertebral column and associated muscles, as well as the limbs and the associated muscles. And salamanders have both. Okay? Now, another thing is that similar to ancestral tetrapods, and unlike us, salamanders have a so-called sprawling limb posture. So the orientation of the limbs has some profound consequences for the types of movements that are actually going to provide propulsive forces. And it's kind of important to keep that in mind because I think it's fair to say a lot of humans, since we're mammals, kind of relate more to the mammalian condition for limbs rather than this condition that's found in many amphibians and actually many reptiles. Okay? So here's another little question to quickly answer. Namely, if the steady undulatory swimming of salamanders is like that of a fish, what would you predict regarding the axial motor pattern and movements? Okay? You can work in 2s and 3s on this if you want. Jot your thoughts down in the next minute or so.
Input instead of just the whole body.
Right to this now.
As it's diagonal.
Everyone signs each other. Not active.
The same muscles, yeah, it's just like a fish.
Okay, let's see what you came up with. Let's start in the back row on that side of the room. Can you give me one prediction?
Like foot and leg contact with the opposite as it.
Axial. How about that side of the room? Back row. So axial refers to the vertebral column. We'll get to legs. I'm glad you're interested in legs. Can you give me something? Back row, that side of the room.
Maybe movement with the tail.
Well, what about tail movements?
Like if it was going through water, maybe the tail could like, help it swimming.
Can you flesh that out a little bit?
Like one side of the tail would be, like, the muscle on the one side would be going in the one direction.
Well, are you talking about movement or muscle activity? Just pick one or the other. Because I just want one thing. I don't want you to worry about having everything covered.
I guess the movement. I don't know, like
How can you describe the movements associated with this?
side to side maybe.
Let's go to the next row up. Can you help us out for the pattern of movement?
Unilateral muscle.
Movement. I'm delighted you're thinking of how the muscles work, but let's start out with movement. Next row up, how do you describe the movement?
Moving side to side, laterally, axially.
Okay, and does that mean I move this way and I move that way, that side to side?
Back and forth, but pushing against, I don't know. Forward.
Do an imitation. You're doing this? What's that?
Undulation.
Yes?
Lateral axial undulation.
Steady.
Okay, in what way do undulations occur? So you could also think of that as lateral bending, right? Next row up.
Posterior propagation. So, just like the fish, the wave's gonna go head to tail.
The propagation of
Muscle activation.
movement. Movement. Put it together for movement.
Is posterior propagated.
Okay. So, got a posteriorly propagated wave of lateral bending, correct? That's what you all were trying to say. But get used to being nice and succinct. Again, these are just the sorts of questions you're going to get on lecture exams. Okay, so now we've got a descriptor of movement, and I'm delighted. We're going to have a whole bunch of things about muscle activity, clearly, next row up. One thing about predicted muscle activity. How about working together with the next row up?
When the tail's like this, the side's activated while the other side is not. So,
That's a tad off the mark. Can you kind of use some words to sharpen that a little bit? What?
Unilateral.
Okay, so does that mean you only see muscle activity on one side of the animal at a time? If it's unilateral muscle activity?
Wait, that's 5.
Pardon me? Was it unilateral muscle activity or not? Who says unilateral muscle activity? Raise your hands. Who says no? Raise your hands. Well, I kind of like yes. I don't know. What's going on with this thing today? Okay? Help. What do we say about muscle activity?
It's like rhythmic.
Well, it is, okay. Oh, jeez, I can never spell rhythm. Is it RH?
Yeah, that's right, yeah.
Yeah. Hope your spelling's better than mine. Okay, both movement and muscle activity are rhythmic, but with respect to unilateral, how can we describe that? What does unilateral muscle activity mean?
Start on one side and moves down, and then the other side comes in with it.
Nope. That is unilateral. What's unilateral mean? We don't want you to just throw around words.
One side.
Pardon me?
One side.
So that means you only activate the left side and then you only activate the right side?
At a given point, like on the body, on one side.
It's a very important caveat. At a given longitudinal location, muscle activity is only on one side. Okay? So it could be up here you've got left side activity and down here you've got right side activity at the same time. That's an extremely important qualifier. And what else? Someone said it. Muscle activity is posteriorly propagated, right? So muscle activity, or EMGs, are posteriorly propagated. Okay?
Is it the same thing like how the muscle, like the EMGs happen before the wave happens? Because you gotta have.
Actually, that is true as well. So if they're in water, we would expect different speeds of propagation of muscle activity and bending, which would result in a phase shift of muscle activity relative to bending. Okay? What's another descriptor for what's happening at a given location?
Alternating.
There we go. You get a pattern of left, right, ad infinitum. Okay? We spent a lot of time covering how fishes move because all vertebrates have a vertebral column. Okay? So we're going to follow through in all groups of vertebrates how that vertebral column is used. And for many groups of vertebrates, it has a very important role for locomotion, and that's certainly the case for salamanders. Okay? You have this diagram on handout 9 that shows you some of the axial musculature of salamanders. Arguably, we see a greater complexity in the axial muscles of extant amphibians compared to the myomeric organization in fishes. Namely, you see some different orientations in layers rather than these myomeres that go all the way from near the skin to the interior of the critter. Okay? And on your diagram right here, you should note that these muscles above this line, which is the horizontal septum, are the epaxial muscles. Okay. And then everything below there is the hypaxial muscles. So that's a name based on the region of the muscles. That's not a specific anatomical name of a particular muscle. Just sort of be aware of that. So that's based on where they are in space. Are they dorsal or ventral to the horizontal septum? Okay? And now if we look at this lower left diagram, if we look at the diagrams on the left, there are two key layers of the external oblique. This layer, which is with basically nothing other than skin removed, is the superficial external oblique, or if you want to say it a fancy way, that'd be the obliquus externus superficialis. Okay? And then this next deeper layer to this, so in this diagram, these guys have been removed. That's the external oblique profundus, okay? Which is just a fancy way of saying that's the deep external oblique. And notice, even though those are different layers, that the direction of those fibers is from a more dorsal anterior location to a more posterior and ventral location. So they are oriented oblique to the long axis of the animal, rather than either parallel or perpendicular to it. Now, once you have removed the external obliques, lacking much imagination, the next deeper layer is the internal oblique. So that should be pretty intuitive. And that's shown here. So in this diagram, this muscle's been removed and this muscle's been removed. And this is the internal oblique. And then with the internal oblique removed, the next deepest layer of the hypaxial muscles is the transversalis muscle. Okay? These also have an oblique orientation, but it's kind of flipped relative to those more superficial external oblique muscles. Namely, you go from dorsal posterior to ventral and anterior. Okay? So that's some of the stuff that potentially can act on the axial structures. Let's first consider swimming in salamanders. And I don't know how many of you have seen salamanders swim. Perhaps it's not at the top of your movie viewing list. But here's an ambystoma larva that is swimming. Notice the gills. So how is it swimming?
Undulation.
Lateral undulation. So when you talk about movements, it's very important to provide the directionality of the movements. Because in theory, you can have vertical bending in the vertebral column. But in fact, we see lateral bending of the vertebral column. And what else happens that's noteworthy?
Tucks everything in.
Right. So they've got legs, but they don't use the legs when they swim. They just are using the axial structure. So it's not as if they're paddling with their legs. They're just doing lateral undulatory swimming. So there's a lot of reason to believe, maybe that's kind of similar to what goes on in fishes. So let's actually look at the pattern of muscle activity recorded from one side of a swimming salamander in the neck, 3 locations in between the girdles, as well as very near the base of the tail. Well, what do you think? What kind of axial motor pattern is this? What pattern of movement was there?
Lateral.
In addition to lateral bend, what about it?
Anterior and posterior.
Propagated posteriorly. Okay. Well, what about the muscle activity? Is it a standing wave pattern or a traveling wave? Who says standing wave? Raise your hands. Who says traveling wave? Raise your hands. Okay. It is in fact a traveling wave. Who says it's propagated anteriorly? Raise your hand. Who says it's propagated posteriorly? Raise your hands. Indeed, it's propagated posteriorly. Notice the significant lag time. You just have these plots of voltage versus time. And if you were to connect these lines, they would be sloping downward to the right. Namely, this gets turned on before this gets turned on before this. Okay? And this is for the epaxial muscles. In a nutshell, salamanders swim using the same motor pattern as fishes, an alternating unilateral pattern of activity that's posteriorly propagated, and it's propagated posteriorly with a speed greater than the speed of propagating the mechanical bend. Therefore, you get a change in the timing relationship such that at more posterior locations, the muscles are actually stiffening the body rather than actively bending the body. This is part of the reason we went over swimming of fishes in detail, is to sort of set up what's going on ancestrally in vertebrates. But indeed, salamanders have more stuff than just these epaxial muscles. They have the hypaxial muscles, as we mentioned before, the 2 layers of the external oblique, the internal oblique, and the transversalis. And this is all left side hypaxial muscle activity. And this is during swimming of a different species of salamander. This is from a different study. And I'm showing you when the body is convex on the left side versus concave on the left side. So if activity occurs only during fiber shortening, you have onset of muscle activity here and offset before here. Okay? So, not all the muscle activity actually occurs during shortening for the hypaxial muscles, although the lion's share of it does occur during presumed shortening of the muscle fibers. Okay? And also notice that those various layers have a lot of simultaneous activity, which sort of makes sense. You know, activate them all at the same time to help bend the salamander to a coarse approximation. So let's just kind of recap then that salamanders are swimming primarily during lateral undulatory locomotion. It's extremely similar to fish, as we mentioned. There's a propagation of a wave that travels from head to tail. In other words, a posterior propagation. Another thing that's similar is actually the amplitude of bending increases from head to the tip of the tail. And then let's consider some of the underlying muscle activity. If we think of collectively what's going on with the axial muscles, there's a propagated motor pattern. And I mentioned it's propagated faster than the propagation of the mechanical wave of bending. Okay, and at a given longitudinal location, you alternately have activity on the left side, and the right side, and the right side, and at a given longitudinal location at a given point in time. You only have activity on either the left side or the right side. Okay? And to a coarse approximation, the hypaxial muscles have synchronous activity, and actually at a given longitudinal location, again, to a coarse approximation, they're active at the same time as the F-axial muscles. Doesn't look like there's much new here, does it? We saw this before. This is old hat. Okay, well, so is it the case that when salamanders move on land, they just wiggle their bodies in addition to moving the legs and everything kind of takes care of itself? Or did something novel pop up during the course of evolution? Well, here are the F-axial EMGs. At the left, the one that we saw for a swimming salamander, and at the right, a walking salamander. So do they just do the same thing on land as in water? What's different?
It looks like they use their neck more than they were when they were swimming.
Let's concentrate mainly on the trunk, okay?
There's no flag there.
Okay, so there's a standing pattern. There's no propagation of muscle activity for terrestrial locomotion. Interesting, so we have a different pattern of neural control that is used during walking, even though during walking there is lateral bending, okay? So there is something new that popped up, okay? Now, if we keep track of what's going on in the hypaxial muscles, remember this is what we found for swimming, and then superimposed on this pattern of alternately bending to the left and the right, we have the left side muscle activity for the external obliques, as well as internal oblique and the transversalis. Is there anything different for the hypaxial muscles in walking versus swimming?
It's not all together.
Absolutely. So those two deeper layers are out of phase. They are asynchronous with the external obliques. This was not expected. This was quite an interesting finding when this study came out. A lot of people are still squabbling a bit about interpreting this pattern of muscle activity. So in theory, this muscle activity during walking could actively contribute to bending. And in theory, this early activity of those deeper layers could also potentially contribute to the later stages of bending. So one thing that can happen is that some of these muscles are involved in bending the trunk. But then a working hypothesis for what's going on with those two deeper layers is that perhaps, and in light of the oblique orientation of those muscles, maybe it actually helps reduce the tendency of the animals to twist, because the animals are putting down limbs that are diagonally opposite each other. That creates a little bit of a mechanical dilemma in theory, okay? So that's out there. Again, this is still somewhat interpretive rather than absolutely pinned down, okay? So, for locomotion of salamanders, something old, something new. Here's the dorsal view of sandy salamander walking. And, as I mentioned, there is lateral bending. But when they're on land, they also move the legs. Now, this gets a little bit complicated depending on how fast the salamander is going. Very often, salamanders just walk. And when salamanders walk, they do not have a propagated wave of bending. They just have a standing wave of bending. So look at this overhead view of a newt. And what I think is really neat about these experiments is, notice here's a side view, and this is water. So the newt is actually starting out in water, and I think you'd be hard-pressed to find a substantial difference between it walking in shallow water and then continuing to walk on land. But you see those very distinct sideways movements as the limbs are alternately moved up and down within a particular vertebrae. However, when salamanders go fast, you can actually get a propagated wave. But it's actually rather difficult to get salamanders to go very fast. So that's not studied as well as the walking of salamanders. Okay? So here's a head-on shot of a newt, which is a type of urodele. And this has what is referred to as a sprawling limb posture. Namely, the feet are lateral to where the limb attaches to the animal. So it's very important to be precise about this. And based on skeletal reconstructions, this sprawling limb posture also characterizes early tetrapods. Okay? And sprawling limb posture does not refer to the limb being bent. It refers to that location of the foot relative to where the limb attaches. Okay? So realize, if you reduce the problem to 2 dimensions, and if you look at the front of a salamander with sprawling limb posture, here's the body, here's the proximal limb, and here is the more distal portion of the limb. Here's the point of limb attachment, here's the point of foot contact. We have a substantial distance between those two. In anterior view of an animal with so-called erect limb posture, you see something like this. So here's foot contact, here's where it's attached, same distance going from the middle of the animal to the side. Now, where this can get tricky and where there are a lot of misunderstandings regarding upright versus sprawling limb posture is, and let's all get out of our chairs and do this collectively. Okay. Our legs, compared to many other tetrapod vertebrates, are quite straight. So as you're standing, when I look at everyone's legs, they pretty much go straight up and down. But now I want you to do a half knee bend. And as we look at each other from the front, your legs appear to be straight, but they most certainly are not straight if you look at the side. So don't mix up those two things. An erect, you sit down now. An erect limb posture does not need to mean a straight limb. It refers to the location of the foot relative to where that limb is attached to the critter. Does that make sense to everyone? Because commonly folks get messed up and they focus in at the amount of bending at this joint. Okay? And it's sort of a classic limb posture, as I've attempted to draw here with my cave art. The proximal portion of the limb is nearly parallel to the horizontal plane. Okay? So, a good way for you to do a salamander imitation is like this. Let's have everyone be a salamander front limb. Okay? Where you've got this. And this is parallel, or excuse me, perpendicular to your long axis. You're good little salamanders. Very well done. Now, I want you to think hard about having a limb oriented that way. And if you have a limb that is oriented like this, I want you to get your heads together in small groups and make a list of the movements you can use with a sprawling limb in order to propel yourself. Okay? Go to it.
It's really a rowing motion. Yeah.
Like,
Good, like,
at
at the same time.
I bend out like you bend over. Like that.
Yeah.
But like I don't know,
Yeah, you're rowing. Like down and back, or like, you can go like up and down.
But what direction do you need the forces to be to propel yourself? Are forces up and down going to propel you?
Pushing back.
Yeah.
Parallel.
You got quiet all of a sudden. You got it all figured out? Okay. Let's start at the back, this side of the room, back row. Give me a movement. The sprawling limb. What do you got?
I guess moving forward, pressing into the ground, kind of.
Oh, you're doing all kinds of things with your arms, and I'm delighted you are, because a bunch of them are correct, but can you isolate a single movement?
I guess.
Get your elbows out. There you go. I like that. Better salamander. Yep.
So I guess pressing your limbs into the ground.
Okay, well, they're touching the ground when you propel yourself, but what's interesting that you're doing with your sprawling limbs is you're going like that, right? And you may have difficulty saying, what's the word for doing that, but you did a great salamander imitation. That is long axis rotation of the proximal limb element. Okay? And that is a propulsive movement. Next row up can come up with another one.
They'd be able to push themselves up to lift their head up.
But for propulsive forces, you gotta push back. So if I'm on the ground and I simply extend my sprawling limbs, that's just doing a push-up. That's not propelling me forward. Not by itself. Okay? Next row up.
You could extend one of the elbows, and then the next one.
Well, you're kind of doing push-ups in a different way, right? You're doing unilateral push-ups.
Yeah.
So in fact, you can extend the knee joint, but it must be combined with other movements. So that would be limb extension. Can you come up with something else? Well, let's quickly scoop through some animations so you can be thinking about this before next class. Okay? The limbs are attached to the girdle is attached to the vertebral column, and remember, the vertebral column bends. So you can actually just hold the limbs like little struts. This is the pelvis, this is the femur, this is the tibia, this is the foot, and you can have pelvic rotation in a horizontal plane. So you can actually use axial movements to move the limb. Another way you can move is to move the limb relative to where it attaches to the body. And if you move the distal part of the limb posteriorly, that's referred to as retraction. That occurs in the horizontal plane for the femur. And then another major movement was the one that you correctly identified back there, namely long axis femur rotation. Now, all these obviously are for the hind limb. Okay? So these are three major movements that are important and contribute to propulsion in sprawling limb vertebrates that don't happen for vertebrates with erect limbs. There's also leg extension in both sprawling limb vertebrates and erect limb vertebrates. So keep thinking about legs, vertebral bending, and before next time, think about how they are coordinated with each other. We're going to put that together next time, okay? And I've got lab handouts and lecture handouts up here. How do you still need those?